The title of the talk is Current Industry Availability of Low Expansion Borosilicate Glass for Mirror Makers by Bart Fried. Bart will discuss the past and current sources of glass for mirror making, lengths and definitions of various name brands for materials and their properties. Ladies and gentlemen, it's my pleasure to welcome Bart Fried.
Good afternoon. Thank you for inviting me. I can promise you this will be the shortest talk of the day. It's a very simple topic, and although I was given 45 minutes, if it takes more than 10 or 15, I've talked too much. Before I get started, I'd like to ask a question from the audience, and don't be shy about raising your hand. I'd like to know who in the audience has the erroneous belief that glass is a super cooled, slow-moving liquid. Raise your hand if you think that's true. Okay, well, the erroneous part should have been a clue. Glass is an amorphous, crystalline solid. It exhibits some characteristics of liquids in certain ways. But historically, people have pointed out to church windows that appear to have sagged over time, and they also look at an elasticity that glass has, where it will bend and hold its shape for a period of time in its bent position, but eventually it will relax back to its natural form. So years and years ago, when they were trying to determine what was the largest size of a lens that was practical for an achromat, and they thought, well, like the Yerkes 40-inch or maybe the 42-inch that the French made might be the practical limit. The reality is that sagging of glass due to flow is not an issue. You have mechanical sagging, that's something completely different. Where does that bring us? Well, it really brings us to the question of mirror glass for amateurs, and what is it that amateurs are looking for, and why am I here talking about this at Stellafane? A couple things. First of all, low cost obviously is important if you're an amateur and you don't have, did I lose, there we go. What good is it if you can't afford it? Also, of course, you want reasonably good performance. And by reasonably good performance, what does that mean? Well, it needs to be easy to work because you're going to do it yourself. It needs to have, or should have, ideally, a relatively low CTE. Now, CTE, for those non-engineers amongst us, stands for Coefficient of Thermal Expansion. And basically what that is it's a scale that measures how much a material will expand and contract at a given temperature and a given change in temperature. Ideally also, the glass that you're going to work with has reasonably good chemical resistance because there's acids in the atmosphere, and you really don't want a mirror that's going to etch easily and be a problem for you. And by the way, we're only talking about glass for mirrors today. We're not talking about lens glass. And the other thing that's somewhat important, which gets back to my very first question about what is glass made of, is it needs to be able to be fine and annealed. Some products do not anneal well. Some don't require annealing at all. But most glass that you're going to use or would consider using to make a mirror needs to have any of its internal stress reduced or eliminated, or you're going to have a lot of problems when you go to grind and figure. You're going to find that it's going to want to move on you. The figure's going to change for reasons that are seemingly unfathomable. And if it's not annealed at all, the glass is going to break at the drop of a hat. In fact, all glass today manufactured for any products goes through an annealing process, or it's extremely fragile. And then finally, it needs to be readily available. I mean, what good is it if it has all these features and you can't get it? And then it's of no use to you. And that's the prime reason I've been asked to talk today. Okay, so what are the types of cheap mirror glass? Well, you have standard soda lime, which is the same material that Draper used for his porthole glass mirrors. It's the material that was used in the 100-inch at Mount Wilson, and it's the material that was used really up until the 200-inch Palomar telescope proved out that it was easy to use, reasonably easy to produce, and not terribly expensive. So those are the two main types. The soda lime is easy to work. It's very easy to obtain. It's as cheap as it can be. It's easy to find anneal, and anneals relatively quickly. But it's affected by some chemicals, so it's not ideal in that respect. And the CTE is a number of around 70 to 90, depending on who made it and some of its constituent elements besides the sand. Now, 70 to 90 is a number that's high. And I won't go into the scale for glass, but 0 is ideal. 0 means there's no expansion and no contraction. And you can buy glass like that. It's technically glass ceramic, and it has other issues. It's very expensive, and it's got other things that make it somewhat difficult to work. But it is available. So you're really looking for something that may be less than 70 to 90, because that 70 to 90 means that as the temperature drops at night, your telescope mirror is going to be changing its shape. And if the temperature drops all night, like it does sometimes here in the east, that means you could wait until 6 in the morning for your telescope mirror to settle down and finally equalize with the ambient temperature and start giving you good images. And this is one of the big problems with some of the early large telescope mirrors. And for example, at Dominion Observatory, where they have a 72-inch mirror, they replaced the original Brashear soda lime mirror with a borosilicate mirror, because they just found that while the original mirror was really good, they spent half the time just waiting for it to cool down and equalize, and they lost too much time. So it was worth making a new mirror for them. So that brings us to borosilicate, or what most people know by the trade name Pyrex. What they don't know is that you can get it in a variety of CTEs, or coefficients. Borosilicates are used for lighting glassware, for example. It's typically around a CTE of 45 to 55. It's better than 70 to 90, but it's still not anywhere close enough to 0 to make it really desirable for a telescope mirror. Borosilicate can be annealed, can be fine annealed. And by fine annealing, that means it's an extra slow process that really allows any internal stress to completely relieve itself. It lets the crystal lattice structure, well, it's not really a lattice, it's amorphous, but it lets the crystalline structure find its natural relaxed state. Borosilicate, interestingly, is also unaffected by most chemicals. You can etch it with hydrofluoric acid, but almost all other acids won't attack it, or attack it very, very slowly. So from an environmental standpoint, it's really good stuff. And it also means that if you're going to recoat it, you want to remove a prior coating, your range of chemicals that you can use for removing the coatings is greater. Now, the beautiful thing about it is it does have some varieties that have relatively low CTEs. Pyrex and the Corning products standardized around a coefficient of 33. So that's, about 1/3 of the upper range of what you might get with soda lime. And obviously much closer to 0. So now we're talking about a product that's going to be relatively stable, not completely stable, but much more stable during temperature changes in your observing room. Let's see if I get this. Okay, so briefly I'll talk a little bit about how you make borosilicate. The original method for making borosilicate was simply to melt it in a pot the way all optical glass was produced in the early to mid-1800s. It was invented, actually, I think in the 1880s was when Schott started playing around with borosilicate products. And what you would do is you'd create these big lumps of glass called boules, and the boules had to be cut. The blanks had to be cut from the boules. And by the way, this method is still used today in optical glass. When our company buys optical glass, we have the option of buying it in large boules and cutting it ourselves, or we can get it pre-cut into slabs. But Optical glass is made a very slow process, and that's why the cost of optical glass is so much more than glass used for making window panes. Now, the next method that's used for borosilicate is pressing into molds. This is a much more efficient way because you end up immediately with a near net or a net shape that's desirable. And especially if you want something like a honeycomb, you can either melt the glass in the honeycomb or press it into the honeycomb shape. So it's more efficient, so it's also cheaper that way. However, it does introduce considerable more stress, and you've got to be a lot more careful about making sure that you have a homogeneous mix and there aren't a lot of bubbles or seeds in it, so that you get a good blank to work the glass, and you're not going to come up with divots in the surface that open up, bubbles and seeds. Rolling glass is how window glass used to be made from about the turn of the century up until the 1960s. And it introduced another facet, which is the continuous furnace or continuous glass tank. Continuous glass tank is a really large vat of glass that feeds continuously into a rolling line in this case and is constantly being replenished on the uphill side, in the back end. So as glass is pouring out in between two rollers, it's being fed back in to keep the tank at a relatively constant level. This is high production glass making, and you're talking about a furnace tank that might be 100 or 200 tons of glass or more melted at a time. It's a reasonably cheap method, and recently rolled Pyrex or rolled borosilicate was available up to about 2 1/4 inches thick. And this is the issue today is that particular line has ceased production, and while everybody's been panicking about, oh my gosh, we can no longer get Pyrex to make mirrors. Finally, in the 1960s, a guy named Pilkington in England developed a float process. That's where you take glass, you melt it in the same type of continuous furnace. But instead of rolling it out into a long ribbon that would then continue into an annealing oven and get chopped up at the tail end, the glass comes out of a large furnace or tank that goes and drops the glass in its molten state, into a vat of melted tin or molten tin. They say, well, why would you pour the glass into melted metal? Well, tin melts at a much lower temperature than glass, but the glass has a lower specific gravity than the tin. So essentially what you're doing is it's almost like pouring hot oil onto cold water. Well, or hot fat. You pour hot fat onto cold water, you have a layer of congealed fat on top. That's exactly how windows are made today and architectural glass is produced today. It's a pretty good analogy. Remember that one. So you have this long ribbon of glass. Again, it's made in tons a day, and it comes out the tail end. It goes again into an annealing furnace, all in one continuous 1/4 of a mile long chunk of glass. And when it comes out the other end of the annealing furnace hours later, it gets sliced and diced into big panels, and that's used for making windows and architectural glass. But fortunately for us, well, I'm going to come back to that for a second. I mentioned that Corning had been rolling Pyrex. Borosilicate was developed by Schott in the late 1800s. The Pyrex brand of borosilicate was founded by Corning around the turn of the century when they discovered that you could cook in this stuff. Now, Schott was making glass for science. Corning made a lot of money making bakeware out of Pyrex because you could keep it in your refrigerator, take it out of the refrigerator because of its low coefficient of thermal expansion. You could then put it into the oven. Coefficient of thermal expansion, when it's low, it reduces thermal shock breakage. And typically you can take borosilicate with an expansion of 33, and you can take it up to about 425 to 450 degrees Celsius, and then drop it into room temperature water, and it won't break. Now, if you try that with a standard glass goblet or dinner plate, you'll have little pieces of glass that just shatter. Okay, so Corning figured out, wow, we can make a lot of money with this, and we're going to call it some fancy name, and they gave it the name Pyrex, P-Y-R for fire. So it's glass that you can put in the oven. However, Corning changed its business model around the 1980s and realized that it really did not want to be any longer in the consumer cookware industry, and they started selling the brand name Pyrex and a lot of the formulas to other countries for different products. And the cookware went to World Kitchen, which is in Pennsylvania, and World Kitchen stopped making borosilicate, but keeps using the name Pyrex. So today, you got to be careful, because if you get cookware made by World Kitchen that's called Pyrex, it's actually soda lime glass that's been well annealed and tempered. And tempering is a hardening process. It also reduces the thermal shock characteristics, but only for a period of time. Constant heating and cooling of your cookware will eventually lose the temper, and then at some point down the road, there's a pretty good chance it's going to break. But Corning also recently discontinued rolling Pyrex, which they did in a factory over in England. These very large tanks need to be rebuilt periodically, and anywhere from 5 to 15 years they wear out. And borosilicate wears out a tank more often than standard soda lime. These tanks are huge and they're very expensive. When they cool down, you have to chip out all the glass from the tank, break it out. You have to break out foot-thick ceramic brick that lines the tank, and then reline the whole thing. It's about a 2-month to 3-month process. And then you've got to charge the tank, heat this whole mass of tons of sand back up and melt it, and proof it for a while until you finally get the mix right. So it's very expensive, it's very time-consuming, and while you're doing that, you're not making a dime on it, you're losing money hand over fist. And you're also not shipping your customers, and they're not happy about it. So Corning looked at their high cost of producing glass in England. They looked at the high cost of relining their tank. They looked at the low volume. It was right at the beginning of this most recent recession. And they said, who needs this? We're just not selling enough of it. They also had competition from Schott, who was making really a superior product by floating borosilicate in thicknesses not quite as thick as the roll material, but the volume was really in a 1/4 inch to 1 inch thick material anyway. So Corning said we don't need it. We also have new competition in China, and we're out of the business. So the only Pyrex or borosilicate that Corning produces today, from what I understand, is they still make labware and they make extruded tubing and real thin sheet stuff, but nothing useful for anybody in this room. But all's not lost. So, Schott, who produced the first processed float borosilicate, still makes it, and it's produced in thicknesses up to 65 millimeter or 2 5/8 inch thick. That'll make a 400 millimeter full thickness blank of 15 3/4 inches. So if you call me today and you say I need a 15 3/4 inch full thickness blank, I say to you, we can get it for you. There is no lack of borosilicate in the market. The question is it as cheap as it used to be? And the answer is no, it's not. In order to make a blank for you, I've got to put it on a water jet machine and slowly cut it. And so it's not as efficient as when it was pressed into a mold and came out, voila, here's your blank. Nobody has to cut it on a big, expensive, fancy machine. However, there are still sources of pressed borosilicate blanks. Corning no longer presses the blanks. They were using the same facilities to do that as they were rolling. However, there are still a few pressing manufacturers left in the U.S., but most are now making only high-end optics. You see some of these tapered or light-weighted mirrors. They tend to be larger and honeycomb. Some of these guys are actually pressing the net shape. Others are pressing a near net and then machining it out. But it's not an inexpensive proposition. Fortunately, though, there are numerous sources for pressed blanks in Asia. This is like a constant good news, bad news. There's plenty of them, but unfortunately, they typically require a high volume, and there's some tooling involved. And then there are no real distribution channels set up in the United States for it. There's a reason for that. But there are industry sources for high-end glass. One of them is Advanced Glass in Rochester, I think in Rochester, New York. And you can see a picture. I'll try your laser pointer here. I don't know if it's working or not. Yeah, right over on the right. They're making near-net shaped blanks. And they'll even do some of the grinding for you. They won't figure it for you, but they can give you a preliminary diamond-generated curve. Okay, so if there's float and pressed sources for borosilicate, what's the problem? Why was I even asked to talk? Well, the problem is there's very low overall demand within the ATM market. And in fact, one of the businesses, Wilman Bell and Perry Ramaklis, who was providing kits for many years to the ATM market, he called me a couple of years ago and said, Bart, I can't get borosilicate anymore. What can I do? And I said, well, can you buy 500 or 1,000? I can't get you 20 or 30 or 50 or 100. So that's the issue. Most mirrors that are made in Asia, that are pressed and that are cheap, are going to the mass-produced telescope makers in Asia. You're getting the benefit of it because you're getting all these mass-produced, inexpensive reflectors that have flooded the market in the last 15 or 20 years. That's where your blanks are. And so the cost is not the prohibitive factor. The real question is, and I don't have the answer for this, the real question is there a business somewhere to be had supplying the ATM market with low-cost pressed borosilicate blanks? I'm gonna make a guess and say probably not. The ATM movement is much smaller today than it used to be, and for someone to put out, $5,000 or $10,000 or $15,000 for inventory that may last a couple of years, I don't think we're going to see it. I know our company certainly isn't going to do it. So if someone wants, 500 or 1,000 blanks, give me a call. I'll have it for you in a couple of weeks. If you need 2 or 3, I can't help you. So that's my talk. That's all I got on borosilicate. Any questions? Well, I wasn't going to give a shameless plug, but I work for Gray Glass. We're in Queens Village, New York. Yes. There's a lot of trade names for different types of glass. Supermax, there's Shot Duran. There is a lot of glass ceramic varieties like Zerador and Servant. These are all high-end, high-performance glasses, and you pay for it. They tend to have very low, or even some have 0, or surprisingly negative coefficients of expansion, where they get colder and they actually expand and not contract. It's kind of weird, how that works, but I guess like water when it freezes. For the ATM, borosilicate, it's great stuff. It's really great stuff. There's no application that I can think of for an amateur astronomer where you need Servant. You're talking about space applications or really, really extreme conditions where maybe you're at the Atacama Desert where it goes from 120 at night to 20 below, or 120 during the day to 20 below 0 at night, or some ridiculous temperature change. And I mean, there's another really great material. I think it's the greatest thing since sliced bread. That's sintered silicon carbide. It's the lightest, strongest, zero expansion material I think you can get your hands on. And it's tough as nails, but it's just expensive as hell. That's what a lot of space-based optics are made out of, because a big blank like this weighs about 3 pounds. Yes? Well, plate is soda-lime. Plate refers to the process that was used actually prior to rolling glass. It was poured out on a big steel plate, and then it was polished on both sides. But it's just soda-lime. It's the same as crown glass. It's, basically crown glass.
There's been a lot of chatter here in Stellafane the last couple years about ways to cool the mirrors.
Well, yeah, I mean, there's been many telescopes I've seen up here where people have fans on the back to try and get but a lot of that also has to do with keeping the mirror at ambient temperature so that it doesn't generate its own air currents within the tube. I think it's probably more air currents in the tube than it is actually trying to get the blank or the figured mirror to equalize with the outside temperature. Anybody else? Yeah? Oh yeah, I mean, I can bring mirrors. Anybody who can go over to China and make a purchase order can buy mirrors. Well, it becomes cost efficient when you have I'm going to say a third of a container load, which is 10,000 pounds. So I don't know how many blanks that is. I guess it depends on what the size is. It's typically thousands because the freight, you get eaten up by freight. And also, frankly, in many companies in Asia, and more specifically, typically China, don't want to be bothered making 200 of this and 300 of that. They want mass production. That's what they're geared for. Not always, but typically. Okay. Thank you very much.